Hello everyone, welcome back to Everything Swift. Today we'll be tackling another Leetcode question, number 35, titled Search Insert Position. We're given an array of integer named nums and also a target parameter of type integer and also the return type we're supposed to return an integer. So let's go through the question to see what we're supposed to solve today. We're given a sorted array of distinct integer, which is this nums parameter here, and also a target value, which is represented by this parameter here, named target. And we're supposed to return the index if the target is found, meaning that we're supposed to find this value, this parameter value in this array here, right? In this nums array. So we're supposed to return the index of that. If in the event we do not find it, we're supposed to return the index where we would like to insert it inside the array that's given to us, right? So the plot twist here is that we must write an algorithm, which is a big O of log n runtime complexity. So now, don't be afraid by this thing, and I'll explain further uh, on why we shouldn't be afraid in this question with this specification, right? So this is actually a hint for us. So the strategy to solve this question is actually using binary search to solve this question. And there are two components to spot uh, binary search question, right? Which this question is screaming binary search towards us. The first one is this keyword here called sorted array. The definition of sorted array here is basically, I guess, is self-explanatory. Like the number of the integers within the array is basically in ascending order, right? Like for example here, 1356. This is basically a sorted array, right? So that's the first component of a binary search that we should pay attention to, sorted array. That's the first tip. Second one, if they're saying that big log n runtime complexity, that is the second component that hint towards us that this question can be solved with binary search. So just keep these two tips in mind. If you see the keyword of sorted array, and especially if they provide this condition here, solved with the algorithm of log O log n runtime complexity, is usually binary search could be the answer towards the question. And basically, that is the strategy for this question. So I'm just going to jump straight into the code, and we're going to see how we're going to do binary search to solve this question. So if you've been following along with my other videos, you know I like to do a fast check to exit out of the function loop just for a small performance optimization here. So what I'm going to do is if nums is empty, right? I'm just checking it if the array is empty. If it's not, if it is empty, sorry, if it is empty, that means there's no value for us to search, right? The target won't exist inside there. In that event, I'll just return a -1 index, which is an invalid index. But since we can't find anything in an empty array, so I think that's fine. So now this code below here is basically a very templated structure to build up a binary search algorithm, right? So the first thing we want to know in a binary search is we have to find the midpoint so that we can keep finding the midpoint in each loop, and then we keep narrowing down our search options in each loop iteration, right? So to do that, to find the midpoint, we need the starting index and the ending index. So first thing we're going to do is basically take the first index, which is index 0. That's the start. And the ending index is basically the count -1. -1 because we are dealing with zero-based index, right? So that's the start and end. Then we're going to do the the while loop, sorry, for us to find the midpoint. So while start is less than equals to n, this is where we compute the midpoint. So mid equals to start, n minus start divided by 2. This is how we find the midpoint. So there are other solutions that I've seen before that does like n minus start divided by 2. And I think in some in some programming language, like this kind of formula will cause an integer overflow. So to avoid that, we're just going to do ms start divided by 2. So this formula here uh, will will avoid the scenario of integer overflow, right? So now that we have the index of it, we want to know the value, right? Whether this mid-val value that we're searching for is equals to the target. If it is, then we'll exit out from this while loop because we have found it and we are returning the mid index uh, since it matches the target, right? So mid-val equals to nums of mid. So here we will check if mid-val equals to target. If it is, then wonderful, we can just exit out from the while loop and return the index, which is mid here. Now, in the event if it's not, the mid-val doesn't match the target, we have to continue this while loop, but we have to reduce our search option, and we do that by adjusting the mid calculation. And how we do that is basically adjusting our start variable and end variable. So for here, we'll check if mid-val is bigger than target, else, right? So if mid-val is bigger than target, that means we know for sure that target is on the left side because the nums, this array here is sorted, right? So imagine that 1, 2, 3, 4, 5, for example, and let's say the mid-val is 3 and our target is 1, right? So target is 1, mid-val is 3. We know that the target is smaller because it's a sorted array. So what we want to do is we have to adjust our midpoint, right? So basically our to recompute in the next iteration, we have to adjust the end index because we want to go smaller now, right? We want to adjust because we know the target is smaller than mid-val, so it makes sense to adjust the index to be closer towards the left side, right? Now, in the opposite event, if the mid-val is actually smaller than the target, imagine if the mid-val is 3 and our target is 5. That means we know that we need to go bigger, right? The mid index has to be bigger because we know the target is on the right hand side of the mid val, right? So in that event, that's where we increment, we adjust the start index to be bigger. And then in the next iteration, the mid index will be adjusted accordingly. So yeah, that's hopefully the explanation helps to see why we're going to do what the code that I'm going to write below. So basically over here, if mid-val is bigger than target, target is on the left side, so we'll do n, we'll adjust the n variable to be mid minus 1. In the event if its mid-val is smaller than the target, that means the target is on the right hand side, we'll need to adjust the start variable. So start equals to mid plus 1. And that's about it. So this combination here, creating the start variable and variable, create the while loop, and then to compute the mid index is basically a very typical binary search formula. So once you do more binary search questions, you can see this kind of formula and you'll probably recognize the pattern, right? So I'll just go ahead and return start here to complete this question. So that's about it. Let me just run the code to make sure I pass all the test case. There we go. Let's do more. Oh, there's only one test case. Okay. Let's go ahead and submit this. Hopefully we got it right. And there we go. That is the solution for this question. So yeah, just to recap, the two components that are key for us to identify whether it's a binary search as the solution is the sorted array, that's component number 1, and O log n. Usually some questions do not provide this condition, but just keep in mind like sorted array, this keyword here is something that you need to pay attention to if you want to use binary search as a potential solution. So yeah, thanks for your time. Thanks for watching. If you haven't already, please subscribe to my channel. It helps grow my YouTube channel. I'll be posting more video like this in the near future. Thanks for your time. Take care and bye bye.